Hello everyone, this is Tulasi Raparla from the Department of Mathematics, Maristella College, Vijayawada. Today my topic is Introduction to Group Theory. Before going to group theory, let us see some basic definitions which will be useful for us to define some definitions in group theory. What is a set? A set is a well-defined collection of objects. The objects in the set are called elements or members of the set. For example, in this set we can write names, numbers, alphabets, etc. Subset. A set A will be said to be a subset of the set S if every element in the set A is an element of S. That is, if A is an element of capital A of the set A, implies A is an element of the set S. So what is an empty set? The empty set is the set having no elements. That means if that set doesn't have any elements, we call that set as an empty set. Finite set. A set A is called a finite set if it contains finite number of elements. Definition of a semigroup. A non-empty set G is said to be a semigroup with respect to addition if it satisfies the following: closure axiom and associative axiom. What is a closure axiom? For any two elements A and B of G implies that A plus G belongs to G. That means as we took our addition operation as addition, by taking two elements A comma B of G, if the result of A plus B is there in that set G, then we say that the closure axiom is satisfied. Next, associative axiom. For any three elements A, B, C, if A plus B plus C is equal to A plus B plus C, then we say that associative axiom is satisfied. And coming to the definition of a monoid, a non-empty set with a binary operation plus is said to be a monoid if it satisfies associative axiom and identity axiom. Associative axiom we already discussed. So coming to identity axiom, for an element small a in the set G, there exists an element small e in G such that a plus e is equal to e plus a is equal to a. That means here, if this condition is satisfied, we call this element E as an identity element of the set G. Here this monoid can also be defined as a semi-group which satisfies the identity axiom is also called as a monoid. Definition of a group. A non-empty set G with a binary operation plus, that is addition, is called a group if it satisfies the following axioms: associative axiom, identity axiom, and inverse axiom. Associative axiom and identity axiom we already discussed. So coming to inverse axiom, for any element A in the set G, there exists some element B in the set G such that A plus B is equal to B plus A is equal to E. Here, if we take two elements A and B of this set, if we add these two elements, if the result is equal to the identity element of that set, then we say that B is the inverse of A and A is the inverse of B. Here, A and B are inverses to each other. Examples of a group: Z, which is the set of integers. Z set of integers with the operation plus forms a group But as this Z set of integers has an infinite number of elements, we call this group as an infinite group. And here, coming to the second example, in this set we are having only 4 number of elements which are finite in number. This finite set with the operation multiplication forms a group. So this group is called a finite group. And if capital S is a set, then A of S, which is nothing but the set of all bijections from S to S, is a group with respect to the operation composition of mappings. Here the term bisection is nothing but a mapping which is both 1-1 and onto. So it is called bijection. A of S is the set of all 1-1 and onto mappings from S to S. So this set A of S forms a group with respect to composition of mappings operation. Next, the definition of an abelian group. A group G is said to be an abelian group if for any two elements A comma B in G such that A plus B is equal to B plus A. This abelian group, we also there is another definition for abelian group. A non-empty set which satisfies the 5 axioms is called an abelian group. They are closure, associative, existence of identity, existence of inverse, and commutative axioms. So here this abelian group is also called as commutative group. Coming to examples of an abelian group, the set of integers with the operation addition modulo n is an abelian group. Here in this group we are having n number of elements. And in the second example, the set with 1, minus 1 with the operation multiplication is an abelian group. Coming to order of a group is defined by the number of elements in that group is denoted by order of G. So if that group is having 10 number of elements, then the order of that group is 10. So here let us see the example of that order. Here this is a set with 4 elements, 1, minus 1, I, minus I. In this set we are having 4 elements. This set with 4 elements with the operation multiplication forms a finite group. As this is having finite number of elements, this forms a finite group. As there are 4 number of elements in this group, order of this group is 4. So thank you for giving me this opportunity. Thank you everyone.